All right. Okay. So as I said yesterday that I will continue for these atoms and electrons and atomic structure. So before that, I hope that you have already checked that the uploaded version of this PowerPoint yesterday from the Canvas, that we have some other things like dimensional analysis, the statistics, or doing calculations. I will talk about those in next lab that will be on Monday at 2 p.m. By the way, all the time that we are talking is at Malaysian Standard Time. So if you are not in Malaysia or in Kuching, so please adjust your clock in a way that we are on the same time. So on Monday we'll talk about it for the first lab about the calculation. Basically, that calculation you would be expected to do in the lab calculation and also in the test or assignment that will be given to you later on. So in that way, so that I will talk about it later. But let's move on to the atoms, structure of an atom. So first of all, we know that atoms are the indivisible component. I mean, is it the general perception that atom is the indivisible component of matter? But not anymore. We know that we can divide atom in many parts, right? Is the nucleus in electron and protons and neutrons, and even you can break the nucleus into more parts. So for us, we will just learn mostly about the nucleus, that is neutron and proton, and electrons. So if we do the anatomy of an atom, that we will see, if we break down the atom, we will see generally, we are not going much into detail that or deeper into it, but we will see that an atom, there are some nucleus and electron clouds. Okay, there are. So in the nucleus, there will be some at the center. The nucleus is at the center, and it's a very small compared to the whole size of an atom, and it is very dense. And the most of the mass, I mean, almost all the mass of an atom is for this nucleus, not because of the whole size, but for this nucleus. So you can imagine how dense it is. Okay, so in that nucleus, there are a proton and neutrons are housed, are staying there. Protons are positively charged, right, in an atom, but neutrons are neutral. They do not have charge, but only they have weight, but they do not carry any charge. And outer side, the electron clouds, their electrons will be situated there, and they are constantly moving. And another thing is electrons are negatively charged, and the electrons if you remember, I mean, if you know that we called here electron clouds, not just an orbital. So in that electron clouds, electrons can be found in a cloud around the nucleus, anywhere in the cloud, not at a certain position. There is a possibility of finding an electron in the cloud, not at space, certain space. Okay, so as Niels Bohr told us that here is the nucleus of an atom, and then electrons, they move around like this, right? Here electron, and then here is another electron, there is another what do you call it, orbital, in that way. But this we understand, or we know that this is not the actual the atom, what it looks like. Electrons are not moving around like the satellite around our Earth. It's not like that. Here, rather, this is a nucleus where this is a positive and negative charge. I mean, proton and neutrons are there. Proton is positive. That's why positive is always shown by positive charge. But around this nucleus there is a cloud. There is a cloud, not necessarily kind of only one orbit, that only electron, and this is a cloud. It can be situated, thick cloud you can find, where the electron, you can find the electron anywhere in that position, in that cloud at any moment. And that electrons are coming close to the nucleus and going out and then coming close. So in this way, it is coming like going and coming this way. So this is, we call the electron clouds, and we can find the electrons in that cloud much more, with some certainty. Okay. And most of the time, here it is the nucleus, and this is the electron clouds. The electron might be here at some point. There is no material thing here. We just consider this is a cloud because electron can be found anywhere in this. So it's all considered cloud, but there is no material thing. So most of the time, most of the atom is an empty space. All right. Most of the atom is empty space because this nucleus is so dense. It is so dense and so compact that it is a very small area. It contains a very small area in relation to an atom. So this is a small area, and then the electrons are here. In between them, it is all empty space. All empty space. But this all empty space, if there is an electron here, it will be the electron cloud here, and in between them, there will be an empty space. So if we, generally speaking, that and an atom is mostly empty, 95, 98% is empty space, right? There's nothing there. Only 2% occupied, one maybe a little bit of electrons, few electrons, and then this nucleus mostly is empty. But this empty space, however, they have their own weight. They have their, these are matter because they resist any changes. Or if we try to make, dissect them, they resist of being dissected. So that is a matter. They exert some force, even though they are mostly empty. They exert some force. So where the force is coming, what is the origin of those forces, and why it is, even though empty, why they are, some are solid, some are gas, some are liquid. We will see this answer of these questions later on when we go more into this unit. Okay, so so I was talking about it, that is mostly empty. Now, for an atom, generally, it does not represent any atom on the periodic table, but generally speaking, this is an atom. And how do we read it? How do we know what type of atom and what is the characteristic or specification of that atom? I'm sure I understand that those of you are from foundation, you are already familiar with it, but bear with me. We are going much into the detail in a short. Okay, so atoms is the it has the what I was talking. Okay. Oh, yeah. When we see on the periodic table, how do we know the characteristic or specification of an atom? Okay. So in a periodic table, if we see, we'll see that the atoms are given in this way, like the proton or mass number. The proton is given on top, and then the mass number is given at the bottom. Okay, let me show you one periodic table in a short. How do I? Okay. Okay, here. So I'm sure that you can. I hope that you can see it like any of them. It's a boron, it's an oxygen, it's a fluorine, it's a chromium, it's cobalt, nickel, zinc. Anywhere you see that on top there is 23, 24, or 5, or 3, or 20. All those are the number of protons. Okay, these are the number of protons, and at the bottom they are mass number. Okay, they are mass number. So as we said that the number of proton, the mass number is proton plus neutron. Yeah, proton plus the mass of neutron together combined, and it produces the mass number of an element. So this is the proton number and mass number. Let's go back to that our slide here, and we see that here for this carbon, there are 6 is the proton number and 12.011 is the mass number. So this 6 is the proton number, and this proton number will never be changed. Okay, because this is, we call this the identity number. Like those of you who have a passport number or your identity card number, IC number, you cannot change that ID or a passport number even by one single digit, right? If you change, this is not you, this is someone else. So in that, I mean, that is the analogy for this. So you cannot change the proton number for any element. Okay, if the proton number is changed, that is not that element anymore. For example, if we change to 7, the proton number, it will not be carbon anymore, it will be nitrogen. Or if we change to 5, it will not be carbon anymore, it will be boron. So proton number cannot be changed. However, the total mass number can be changed. Okay, atomic weight can be changed, and that atomic weight is the summation of this proton number plus neutron number. Okay, the weight, sorry, proton weight of that total number, neutron and proton. So atomic number is, it can be changed. And now since we know that the proton cannot be changed, so the neutron can be changed, the number of neutrons can be changed. And when the neutrons are not the same, we call them isotopes. Okay, for an example here, for example here we see that carbon is 12 and 6, 13 and 6, 14 and 6. That means this carbon has 6 proton and 6 neutron. 6 plus 6, 12. This carbon atom has 6 proton. Of course, it should have 6 proton, cannot change. But this one has 7 neutron. Here it is 8 neutron. That means the neutron number has been changed, and that is why they are the isotopes. Almost all the element on the periodic table, they have different of isotopes. It depends on their on the environment or the origin of that element, and the different type of environment they can be found. Based on that, the isotopes are, depends on those factor, the isotopes. Okay. All right. Now we go to a table here, and this should be very similar, I hope, or familiar to you. Now let's try to, fill it up. This, I will not go do all this thing, but just explain a bit. So here for sodium, Na, that is 11, we understand that this is the number of proton, right? This is number of proton, and this is proton plus neutron or atomic weight. mass number, okay, atomic number. So here number of protons, it is already given is 11. Okay, I know it is already given here is 11, and then number of neutrons will be the balance from 20 minus 11, the rest of it, the balance of it. So it will be 9. Number of neutrons is 9 here. Number of electrons, since we see there here for this element, it is considered it is 0. There is no charge here, right? There is no charge here, is considered 0. Zero charge, no charge here. That is why it is neutral. So we know that protons are positively charged and electrons are negatively charged. Now, this element tells us that since there is no charge on top, there should be equal amount of positive and negative charge. I mean, the balance is nicely, nice and steady. It's nicely balanced. There is equal number of positive and negative charge. That means one proton will carry one positive charge, one electron will carry one negative charge. That means it has 11 proton, so it should have 11 electrons as well. That is why, and that is how it should be balanced. There will be no charge. For this case, we see, of course, it should be 11. If not 11, then it is not a sodium anymore, right? So there will be 11 protons here, but how many of these neutrons? How many neutrons will be there? It is not 9 anymore. It is 11 again. I mean, now for this case is 11 because 11 plus 11 is 22, isn't it? And in this case, now we see that this element is carrying a positive charge. Carrying a positive charge means this positive charge of the electron, the proton, has not been balanced, or it is not equal to the electrons it is carrying. That means it has one negative charge deficiency, and that is why it is positively charged. That means it will have 10 electrons here, not 11. If it were 11, it would be just like this, no charge. But since it is positive 1 charge, it is showing, that means it has 10 electron, and 10 electron neutralizes 10 proton, but 1 proton extra, it is showing this positive charge. For oxygen, it's already given oxygen, right? Oxygen is O, and it is carrying 2 negatively charged, and it has 17 this atomic number. So the proton number of oxygen is 8. Of course, it cannot be changed. Even it is not given, we know from the periodic table or from the oxygen that for oxygen is 8. That means it's kind of, it's identity card number. So oxygen is 8. Even nobody tell me if, since O is given or oxygen is written there, I know this is 8. And the balance is this number of neutrons, and then it is 2 negatively charged. That means it was suppose it is 8 is here, it is carrying 8 proton. So 8 proton should have 8 positively charged, right? But it is carrying 2 excess negative charge. That means it has 10 electrons. It has 10 electron. That means 8 electron neutralizes this 8 proton, that is positive and negative charge, but 2 excess electron it is carrying. It is having that excess charge of these two, from these 2 electron, and so on. You can try to figure this out. And for this case, I tell you that this is here, it is not given, so we have to find out what is the element for this, and what is the state of this element. Like this is 78 number of proton. From 78, if we say, we will already understand, if we look at the periodic table, it is 78 is platinum, okay, and then is it platinum or plutonium? Let me check. Yeah, it's platinum, and then it is 117 is number of neutrons. So the the mass of this will be 117 plus 78 plus these two, and it will be 195. 195 here, and 76 electrons are there, but as 78 protons are there. That means it will carry 2 positive charge, because 76 electron negative and 78 positive charge. So 2 positive charge extra or excess is staying there. So that means this platinum is carrying 2 positive charge and 78 here. Okay, in this way we can find out the thing. Now we're talking about the atomic mass for quite some time. So what is an atomic mass? This is the mass that is defined by, is expressed by AMU, that is atomic mass unit, and it is by definition that that carbon 12, that is 12, the carbon has many isotopes, right? So the carbon 12 isotope, that one has 12. How much weight, atomic weight it has, exactly the weight the carbon 12 has, is called the 12 AMU. So the 12 AMU is the mass that carbon 12 is sharing, or it has. So it is the standard for the 12 AMU, and the other elements are matched and referenced against this carbon 12 AMU for the mass, atomic mass unit. Okay, and average atomic mass is weighted average of the all naturally occurring at isotopes in the element, because just now we saw here that atomic mass, it is actually number of protons, right? It is number of protons plus number of neutrons. Okay, I'm not writing number of neutrons. So this is actually, it is this, the sum of this proton and neutron. So proton and neutrons, they are the whole number. You cannot have a 0.1 proton or half of a proton or half of a neutron. There are integers, there are the full numbers. Okay, there are full numbers. You cannot have half or a fraction of it. So if we do not have half or fraction of it, how can we have the fraction of this number, of total number? All right, how can we have the fraction of this total number, where it is coming from? So this is the question, and the answer of this question is this proton and the atomic mass number is actually the average atomic mass of all the isotopes that occurs naturally for that element. For carbon, we know that there are 3 isotopes, carbon 12, 13, and 14. For others, for hydrogen, there are 2. For oxygen, there are 4. All those isotopes are considered accordingly for this, to measuring this atomic average atomic mass. All right, and that is why we see that's the fraction here. If we did not consider the average atomic mass, of course it will be only, we have to express this carbon 12, something is carbon 14, always like that. But on average, carbon is carbon 12.01. And this is also telling us that how close it is to 12. That means 12 is the most prevailing in nature. 12 is most prevailing in nature. And if we do this type of pie chart and statistics, we will see that carbon 12 occurs 80.99%, almost 99%. Only 1% is carbon 13, and a very small 0.001% of carbon 14 occurs naturally, and that is why it is the average atomic mass is 12.01, is very close to 12. How do we find for an atom the average atomic mass and calculate this the mass number for this for any element is from this example we will understand, right? So the atomic mass of two stable copper isotopes, that is 69%, one occurs in 69.09%, another occurs 30.91% in nature. So that copper isotope you can find in nature 69% one, and another one is 30.91 or 31% you will find, okay, in nature. So those that you are finding in 69% has a atomic mass unit of 62.93, and another one that is occurring 30% or 31% in nature has an atomic mass unit of 64.92%, AMU. This AMU that I was talking is in respect to this carbon 12. Carbon 12 has 12 AMU, right? Carbon 12 has 2 AMU. Just now we saw it. Carbon 12 has 12 AMU. So in respect to carbon 12, they will have 64.92 AMU. Another isotope of this copper will have 62.93 AMU, and they are occurring in these two different what do you call it, percentage. So how do we find what is the average atomic mass for copper? All right, of course you can just look at the periodic table, you will find it right away, but if we want to know, if we want to satisfy our intention or our curiosity, how do you find it? It is easy. We have to find out the fraction of this abundance in nature. So we see that it is 69.09%. So it means that it is 0.6909, or we just divide by 100%, right? So that we get this, and this one also we divide by 100, so that we know this is percentage means 0.3091 of copper 1 isotope is abundance in nature. And now after that we will do this fraction. We will multiply with this AMU with the respective abundance. So since it is 63, right, 63, that means this one 62.93, so it is rounded up to 63. So what we'll do is we will multiply it with the 63 here, right? And same goes for this 65. We multiply this, and then we find the average one. The sum of this will be 63 point something, 63.55, right? So this is the average mass unit of this copper element in nature that we find it altogether considered. And if we check in the periodic table, we will see that it is the same thing, 63.5 in the periodic table is given. Okay, so now since we already know that this is the atomic mass unit and then average atomic mass, how it happens, there will be two more things, and these two things are very important in all calculations that we will do in our chemistry things, and not only chemistry. Later on, when you do the chemical engineering calculations, these two things will be very, very important thing. I mean, aspect. That is the mole number, okay, and Avogadro's number. Actually, the Avogadro's number and the mole is very intertwined, is very related to one another. The mole is a unit to count number of particles. All right, it is not a concentration. It is not a concentration. Most students confused with the idea of mole and concentration. It is mole itself is not a concentration, but it is a measure, tool to find out the concentration. But mole is a unit to count number of particles. How many particles are there? We can find if we know the number of moles of that compound or element in that system. And 1 mole of an atom or any compound or element or anything, 1 mole of anything will have as many of atoms as there is exactly in 12 grams of carbon 12 atoms, okay, in carbon 12 element. So 12 gram of carbon 12 is equal to 1 mole, right? Consider 1 mole, and in 1 mole there is always Avogadro's number of particles there. So in this there will be one Avogadro's number of particles. Okay, Avogadro's number of particles will be there. And this Avogadro's number is a constant number. It will never change. And it is 6.022 or 023, sometimes we write, times 10 power 23rd. So in any 1 mole of anything, if in 1 mole of copper, sodium, sugar, orange, 1 mole of what? 1 mole of data, that means now we call it 1 megabyte, gigabyte. So maybe we can call 1 mole of byte. So everywhere it will be this number of that component inside. If we call 1 mole of sodium, in that sodium there will be Avogadro's number of particles there or atoms there. If we call this 1 mole of water, okay, if we call 1 mole of water, in that water, this Avogadro's number of water molecule will be there. Not only hydrogen, but hydrogen and oxygen, both together, water, right? So in 1 mole, there will be Avogadro's number of water molecules will be there. So this is the Avogadro's number and number of moles things we consider. And now here is a thing that in the picture we see this is carbon, of course, black in color, is yellowish in color is sulfur, copper, iron, and mercury. So in this picture there are all 5 different, total different elements are there. One is liquid, one is solid, 2 solids and 2 powder. So these different phases there are there. All of them 5 are in 1 mole. Okay, 1 mole are there. 1 mole of carbon is here, 1 mole of sulfur, 1 mole of mercury, 1 mole of copper, 1 mole of iron is there. Now there are 2 things here that how many individual atoms in each element. Okay, how many atoms of carbon will be in here, how many atoms of sulfur will be here, iron will be here, and copper will be here, and of course mercury is there. So how many atoms will be there? Of course it will be Avogadro's number, right? Avogadro's number of atoms of carbon is there, Avogadro's number of sulfur is there, Avogadro's number of copper are there, Avogadro's number of iron are there. So all together is 6.023 power 10/23. So this is the common between them, right? All of them are having this number of atoms in them. But can anybody tell me what is the difference between them? What is the difference between them in one single unit? Can you think that this is the difference between them? Yes, Jonathan, thank you. This is the difference that between them, the only difference, not only difference, that the remarkable difference actually, the weight of them. This iron will have 55 gram, this carbon will 12 gram, the mercury will have, although it's small, but 207 gram, and sulfur 32 gram, and copper is 65 gram, right? So what is the, I mean, what is the problem? Why is that so much difference between them? Can anybody tell me what is the difference between them? I mean, why is the difference between them? Can anybody tell me? Why is the difference? Okay, molar mass, particle size, molar mass, molar mass. Thank you, those who replied. But the thing is, yes, molar mass, and of course, particle, not size, but the characteristic of the particle. But let's consider first that molar mass is the thing that is making the difference. But then the question, I mean, the answer is not what do you call it? This is, our answer is not 100%, or we have not fulfilled the question to satisfy the question by answering the molar mass. What is making the difference between them, the molar mass? And if we consider the particle size, how is the particle size is contributing to this different weight? I cannot see your chat box. How can I see the chat box? What is, okay, no question, no answer so far. What are the things that is making the difference between them? The molar mass. In one way, I can tell you that this is the density between the atoms they are having in it, right? In one atom, carbon is having 6 proton, 6 neutron. In one atom, somebody, structure, yes, precious, yes. Structure in a very broad way, but I'm taking it a very specific way, that in one atom, carbon is having 6 proton and 6 neutron. In one atom, mercury is having how many? Mercury is having, let me check on the periodic table. I cannot find it now. Mercury is 80, yeah? Let me check. Yes, thank you. Wow, so good that you found it, Jonathan. So yeah, mercury is having in one mole, one atom, mercury is having 80 protons and 80 neutrons. And then uh, for carbon, it is having only 6 proton and 6 neutron. So this is the thing that is making the difference. And since the number of protons are increased, right? The number of protons increased. And for example, for iron, it is housing 26 proton and 26 neutron in it when it is neutral, right? So 26 proton, 26 electron, 26 neutron, it is housing in one single atom, whereas carbon is housing only 6 proton and 6 neutron and 6 electrons in one single neutral atom. But for iron, it is having 26. And since iron is the number of proton and neutron is increasing, so we can see from here that iron is the size of iron, more, the weight of iron and the size of iron is more. And for carbon, the size of the carbon is less and is powdery. Okay, it is solid and something like that. But does it answer all the question? If iron is so big, just housing 26, 26, why this mercury is housing 80, but is still not that big, and then it is almost liquid? So this is another question. That question has not been, it's not resolved, right? It does not satisfy our quest for this type of knowledge. And to understand it, to know it, we will discuss more about it, how the structure changes, or what is the criteria of the structure, and then the differences between the structure, and then their the material. Okay, so why some of them are so solid and heavy, and some of them are powdery and then gaseous. So we will discuss more about it when we study the periodic table next week, hopefully. Okay, so the molar mass, I think we already talked about it a bit. And this is the molar mass. So molar mass is mass of 1 mole of substance in gram, and then the unit of molar mass is gram per mole. When we say that 1 mole of the substance, it always comes as that 1 mole, then how many gram in 1 mole? So it is molar mass we express is in gram per mole. Because mole, we understand by now that in 1 mole there will be Avogadro's number of the component or particles or atoms or molecules or humans or whatever. In 1 mole there will be Avogadro's number of those matter. But depending on the matter, since just now we saw that carbon and hydrogen, carbon and mercury and iron, so it depends on the structure and the matter, the gram or mass of that compound will change according, depends on the structure, if we express in molar mass. So gram per mole is the unit for molar mass that we have to express, and we have to always write in that way. Okay. For any element, its atomic mass is the molar mass and is the gram. And let's say that's given one carbon 12 atom is 12 AMU, that we have already seen it, 12 AMU, one carbon atom, and one AMU is considered 1.67 times 10 to the power negative 24th gram. 1 AMU is, this is the gram, and is extremely small. And 1 mole of carbon 12 atom will have 6.0223 times 10 power 23rd atoms. That is the Avogadro's number. So if it is all given, what is the molar mass of carbon 12 in gram? Of course, we know it already, but if we want to express it in or try to find out through the calculation, how can we find out what is the molar mass of one carbon 12 atoms? And we, of course, we can find it in many different ways, but the thing is, we will try to follow this unit conversion method, right? Dimensional analysis or unit conversion method. So this is, it is asking us that in gram. So what is the molar mass of carbon? Molar mass of carbon 12 in gram. It is asking in gram. So molar mass of carbon 12, we have to find it. And we know that it is gram per mole, right? Just now we said it's gram per mole. And it is specifically told us that is in gram. So we have to find it in gram per mole, not milligram, not kg. Okay. So molar mass of carbon 12, we find that it is gram per mole. And since we need this gram, so this gram should be in the numerator. It should be on top, on upper numerator. Denominator is the mole that should come here, of course. That's a gram of carbon 12 is how many moles, or 1 mole is how many grams. So for the unit conversion factor, we just put these values, or we see this information here, we put these values here. One carbon 12 atom is 12 AMU, 1 AMU is this grams, right? And then 1 mole is Avogadro's number of atoms here. But in this way, if we do, and then we cancel out all those things, atoms, we see that it is mole per gram. Mole is the numerator and the gram is the denominator. So it is not the way that it is, the question is asked. It is asked gram per mole, right? It is asked gram per mole. So we have to inverse it in a factor level calculation. So we have to inverse it. And since it is inversed, everything will be inversed. And we have to write in that way so that we can find, or we can get the desired unit that has been asked, or we need the desired unit for other calculation or for this calculation. So in a way, we have to put it so that the final calculation is gram per mole, or for other calculation, other unit, whatever is required. Let's say it is degree centigrade over minute, right? Over minute. So we have to find in a way that it is always, we are keeping this degree centigrade and in the numerator and minute in the denominator. So in this way, we have to formulate smartly so that we can find the asked unit in a way that we want it to be. And now in this case, if we cancel out all those units, right, all those units, we will see that it is gram per mole. It is gram in the numerator, and this mole is denominator, so it is gram per mole here, and just 12 gram per mole. Okay, so there are some other examples. Another one, it says that the zinc, a silvery material and metal, and it is used in making brass. Okay, brass is mixed with copper, and then it will be mixed with brass. And copper is what color? Copper is a reddish something color, and zinc is silvery color. But when it mixed together, it becomes like a gold color, and sometimes it's it'll be confused with gold. So now the question is asking that how many gram of zinc are in 0.356 mole of zinc. All right. Now, number of moles of the zinc is given, and we have to find the gram of zinc that we should have in this number of moles of zinc. For this problem, we have to find the molecular mass or atomic mass, sorry, for this zinc, atomic mass of zinc. And from the periodic table, we see that zinc is 65.4 or 65.5 in if we just round it up. So 65.4 of zinc is gram in 1 mole of zinc. There will be 65.4 gram of zinc in 1 mole. So that if we just do the unit factor level calculation, and then we will find that how many moles of zinc will be there. Since 1 mole of zinc is 65.4 gram of zinc, but if it is asking that gram, right? It's asking how many gram. If we take in this form, we will be not satisfying the need for the problem, because the gram is in the bottom, the numerator. So if we put here the gram is not coming up, and then we are not expressing it is in gram. So we have to inverse it. That means 65.4 gram of zinc in 1 mole of zinc, and then 0.35456 mole of zinc is from here is 23.3 gram of zinc. From here we find it, right? Another example is here, and I think I'll try to finish. Yes. Okay. Sulfur is saying that it's non-metallic element, and that is present in coal, and coal is burned, sulfur will be converted to sulfur dioxide. Eventually, it comes down in the rain, will produce sulfuric acid. So how many atoms? Now it is not moles, not grams, but atoms. That means single atoms of sulfur in 16.3 gram of sulfur. How many atoms there will be in 16.3 gram of sulfur? Our only clue is in 1 mole of sulfur, there will be Avogadro's number of atoms, isn't it? 1 mole of sulfur, there will be Avogadro's number of atoms of sulfur. That means 6.023 times 10 power 23rd atoms of sulfur will be in 1 mole of sulfur. So from here we understand that since it is asking us number of number of atoms, or how many atoms, or number of atoms anyway. So in this gram, we cannot go directly from gram to atoms. We have to go through via number of moles. So 16.3 grams, because 1 mole of sulfur only can, if we have any number of moles, like 0.2 to 0.0001 mole of sulfur, even we can find out the number of moles. But from gram, we cannot. So we have to go via number of moles. And 16.3 gram of sulfur means how many moles of sulfur, right? From the periodic table, we know that sulfur has 32 gram per mole of sulfur. So from here, we do the unit level calculation, and then we see that here it is 0. First of all, okay, let me, from here we find the number of moles, right? If we divide 16.3 by 32.07, it will be around 0.5 something. Okay, it will be 0.5 moles of sulfur are there. So if 0.5 moles of sulfur are there, if 1 mole of sulfur has this number, this many of atoms, 0.5 will have, we can just multiply it and find out the number of moles, and this is what it happens. But since it is a unit level calculation, we have to put the units in the accordingly. All right, we have to put the units accordingly, and from here it is showing that this is the number of atoms we can expect, or we will have in 16.3 grams of. Okay, I will finish with this. Just to show you that how many hydrogen atoms are in 25.6 gram of urea is there. And this is the molecular formula of urea. It is, so far we have seen only sulfur and what else? But for this now, it is a molecule. It is not only one single element is there. There are many, many different elements, nitrogen, hydrogen, carbon, and oxygen. So altogether is a molecule, right? It's a molecule. And if we write it, is this 2 means there are 2 NH2, right? So if we write it in a separate way, we will find in this way. We can write it in this NH2, NH2, and then CO, sorry, in one CO and then 2 NH2. So that means in one molecule, one molecule of one molecule of this fertilizer, there will be 2 nitrogen, 1 hydrogen, 1 oxygen, but there are 2 plus 2, that is 4 hydrogen atoms. So 2 nitrogen atoms, 1 carbon atom, 1 hydrogen oxygen atom, but 4 hydrogen atoms will be involved in one molecule. So that is how we can say that, okay, in one molecule, that's 4 hydrogen atoms. So 1 mole of urea, there will be 4 moles of hydrogen atoms. Okay, not molecule, but for hydrogen atom, ATOM. So in one molecule of urea, there will be 4 hydrogen atoms. Always. So in this way, the question is how many hydrogen atoms present? 5.6 gram of urea. So again, there is no direct way to go to that atom, but we have to go through a number of moles first. How many number of mole of 5.6 gram of urea makes? So 26 point, how many moles it makes is, we have to find it from this, that 1 mole of urea is 60.06 gram of urea is 1 mole, and then 25.6 gram of urea is making how many moles of urea, and in 1 mole of urea there are 4 moles of hydrogen, and from their unit level calculations we find that the 1 mole of hydrogen is actually this Avogadro's number of hydrogen atoms. So from here, 4 moles of hydrogen is actually how many hydrogen atoms. So this is the answer for this. We'll find. Okay, so there are some other example, 4.6, and then 4% composition. I will talk about it a bit, and then I will directly go to the more structure of atom with the electrons and the orbitals and all those things. So far, do you have any question? Anyone? Anupaja said, sir, is it a must to include units in the calculation, or is it fine if include the answer? No. You please, when it is asked you to show the unit level calculation, please include units in all the steps. Okay, this is a test. Some of you may know it very good, and some of you actually are very master of it, but please still we need to show, you need to show it as if it is in the question. Okay. All right, so is there any other question? Is there any other question? Anyone else? Okay, so thank you for attending the session. I will see you on Monday, 2 p.m. Malaysia time, of course. And just one announcement that I will post, for this lab coat matter, First lab, you don't need it because first lab we will be doing online, so no lab coat is needed. But for the next lab, if we go face to face and if you want to come to the lab, then you have to have your own lab coat. So for the lab coat, there are some supplier in Kuching. I will put it on the on Canvas announcement section. You can find the number of supplier from Kuching and you can contact directly, or you can buy it online from Lazada, from Shopee, whatever, on your own. And because we will not need the lab coat next week or next week, because we have lab every alternative week, right? So that you still have time to think about it. Okay, all the best. Thank you. If you have any other class, you may need to leave now. Okay, thank you very much. Thanks a lot. Yeah, you're welcome. Thank you. Bye-bye. Yeah, Clarence. Yes, yes. You also need a safety glass to order from the supplier as well. Okay, and I will announce it on the announcement section, and you can find the supplier as well there. So the safety glass and lab coat you should buy, and of course you have to come with the full trouser and the shoe. I mean, toe covered shoes, and yeah, that's the thing that will be needed. Thank you for the questions.